Hi, I'm Jonah Comstock, Editor-in-Chief at pharmaphorum. I'm joined by Adrian Woolfson and Kaihang Wang of GenYro. They have some really exciting news. It's actually, as this is published, it will have just been announced or published in a paper in Nature that is going to be a major game changer for gene editing and gene writing. And I will let Adrian and Kaihang tell you a little bit about that.
Yeah, so up until this invention that we have just announced in Nature, assembling DNA has been a major problem in the sense that it takes a long time to assemble it, it's expensive to assemble it, and you can only assemble about half of the human genome because the rest of it's very complex. Our technology introduces the concept of page numbers into the assembly of DNA, and this enables us to assemble any sequence extremely quickly and at a really low cost. So essentially we're democratizing the process of DNA assembly or construction, if you prefer to call it construction. And this really frees up scientists and the biopharmaceutical industry to build anything that they like. And until now, there's been a big disconnect between the ability to design DNA using AI and the ability to construct it. And this technology really kind of bridges that gap and enables a kind of feedback cycle between design, construct, test, feedback. So it really kind of empowers AI, but also enables other areas of the industry like gene therapy or, for example, oncolytic viruses or various other areas to build whole genomes or to build polycistronic constructs or anything big. So we enable big biology, and by bringing down the cost basis and hugely compressing the time to build things, it just makes the whole enterprise of engineering and writing DNA feasible on grand scale.
So tell me a little bit about how it works and in sort of the most layman's terms you can manage.
100%. I can give a bit more technical details, right? So conceptually, there are two steps, right? So the first step is making very, very short synthetic DNA called oligos. That has been cracked in 1970s. Got Nobel Prize, right? From 1970, 1980 till today, 40 years on, right? That has been the oligos. Oligos is a Greek word for short, right? That has been very, very cheap, readily available in huge amount, right? But the problem for that is the oligos, as the name indicates, is very short. It's not long enough for anything useful at all, right? For individual genes, gene cluster, and all the way to the genomes, you really, really need to stitch together these oligos to longer and functional DNA. And that has been a fundamental bottleneck, not just for like 4 decades in kind of engineering, but it has been a problem for there forever, right? So what we have done is really trying to rethink the entire problem of the construction, DNA construction, using oligos as the commodity input to build any and every DNA, regardless of the length, complexity, right? At low cost, high throughput, everything checks, right? And the trick is conceptually very, very simple conceptually, right? The oligos is kind of equivalent of printed pages, right? After the invention of the Gutenberg printing press in the 1440s, right? But the conceptual interesting thing is, in order to have a book, not only you need to have the printed each individual page, you also need to arrange them into the correct order to form the book, right? And before us, the DNA construction is kind of like in the era of you have the printing press, but you don't have another thing called a page number to actually align and assemble the books in the right order. The oligo in this is the equivalent of the pages, the genes, gene clusters, and the genomes, like the books, right? Without a page number, you cannot really assemble the pages, right? Without the DNA page number, people really struggle to stitch together the oligos to functional long enough DNA, right? So conceptually, gonna skip all the technical details. Let's go to the conceptual philosophical equivalent. Is we invented the equivalent of DNA page number. They absolutely guide the construction, but without being part of the final synthetic DNA, right? Because of that, we really destroy all the limitations, right? Essentially, we kind of lacked, we already made a quantum leap, kind of like from a 2D world before to like a new 3D world for the DNA construction. So all the limitations, all the restraints, all the impossibilities before just does not apply to us anymore. Right. So that is a fundamental power of this new technology, which we call.
So fundamentally, this enables you to turn DNA into a programmable material and into a predictive engineering material. And in conjunction with this technology, which we call Sidewinder, by the way, because the oligos go up on the side of the top strand of DNA. In conjunction with that, we're also working on genome language models, which enable us to learn the language of life. So that therefore to design DNA at scale, including small genomes at the moment.
So what's the sky the limit of this technology? I mean, if you're able to write DNA more or less from scratch, you can create whole new organisms, or
I think you are spot on. Sky is the limit, right? So conceptually, right? So Adrian, I want to hear Adrian. Right? So what we are trying to bring here is a synergy between the power of design by AI and a new next generation ability to realize whatever can be designed in real biology through construction of DNA.
Yeah, and I think the really interesting thing to appreciate is that up until now, we've been constrained by the tree of life, by what evolution has given us. And so evolution itself and gene editing all modify pre-existing designs which have been passed down from the inception of life 4 billion years ago. And gene editing, with all of its strengths, and there are many of those, and therapeutically we've seen some wonderful advances, and it's a great technology. But at the end of the day, gene editing red lines text, it red lines genomes, it edits them, right? What we're able to do now with this new technology is reimagine genomes from first principles. So we go beyond the tree of life and enter the forest of possible life. And within the forest of possible life lie all kinds of incredible therapeutics, which would never have been realizable without a technology that can write them de novo. So we kind of close the loop between the ability to use AI to go deep into sequence space and explore that latent possibility. And we conjunct that with the ability to actually physically land anywhere in DNA sequence space with this time machine, which is Sidewinder, our technology, that enables you to travel there and build that sequence, however big it is, and then realize it in the real physical world and use it for the benefit of humankind, whether it's therapeutically or to make biomaterials or do biocomputing or bioinformatics to store and archive information. There's so many uses. So essentially it enables us to define a phase transition in the history of life. It's that fundamental, and unlock what we believe will be a multi-trillion-dollar economy, a bioeconomy, in which biology becomes infrastructure and embedded into almost anything that you can think of, including clothing, and as I said, computing, storage of information, bioenergy, but all kinds of biomaterials, healthcare. There'll be huge implications, and the kind of, I mean, you've seen, for example, recent work where people are using transposons, integrases, and they're capable of putting significant amounts of content into the genome therapeutically. So we won't just be putting in genes, we'll be putting in gene circuits or perhaps even whole metabolisms. So this will take genome engineering to a whole new level and also enable the optimization of cassettes to be, perfectly suited for their purpose, but also regulated.
Yeah. So I want to echo what Adrian has been saying, especially regarding AI, right? So we see the rise of AI in the past 2 years, right? So one powerful thing about AI is especially the modern generation of the reinforcement learning. It can basically feed on its own success, right? But when you are applying the AI to like a computer game or a board game like the AlphaGo, right? It is easy to do that reinforcement loop because you get the readout in silico in computer right away, right? But that is also a fundamental challenge of applying AI in biology because, right, in order to validate, in order to do that feedback loop, right, for the reinforcement learning, you really, really need to kind of validate and test these AI designs, not just in silico, not just in computers, but actually in the real world. And that is a fundamental challenge because you need to construct the DNA to embed the design. And before, that has always been a fundamental limitations. Right. So what we really the first time enable is this fast feedback. For anything can be designed by AI, we can just match the scale in the realization.
Yeah.
So then you just not just do it once, not just do it twice, but the wheel of progress goes on perpetually. You design, you construct, right? Then you feedback on and on and on for anything and everything.
And from a bigger picture, sort of helicopter historical view, you know, we learned how to read DNA, we learned how to write DNA, and now we're learning how to author DNA. We're becoming the authors of genetic sequences, and that gives us tremendous power. And with tremendous power comes tremendous responsibility, which is why we're considerably invested in ensuring that this technology is used safely, and that we're able to screen sequences to ensure that there are no biohazard issues associated with them. But we're tremendously excited by this. You know, the Nature paper is the first of many, and will be followed by several other papers where you'll see there's some new innovations beyond that, which will have tremendous consequences for humanity's ability to use DNA as a technology, as an infrastructure, and to tremendously impact healthcare.
Yeah, as a predictive and about basically turn DNA into a predictive engineering material.
Well, that's really incredible stuff, guys. Looking forward to seeing the paper for myself and everything that comes after. Congratulations.
Thank you very much.
Thank you.
Pleasure to meet you.